The next thing we're going to look at in this section is Theorem 5.12, which is the net change theorem. The definite integral of the rate of change of a quantity f prime gives the total change or the net change in that quantity on the interval a to b. For example, if we wanted the net change of a function capital F over a to b, that's going to be the definite integral from a to b of its derivative. That's f prime capital of x dx, which we know from the first fundamental theorem of calculus would be just f of b minus f of a. One way to illustrate the net change theorem is to examine the velocity of a moving particle along a straight line, where s of t is a position function at time t. Then its velocity, which is the derivative of position, would be given the total displacement as follows. It's the definite integral from a to b of v of t dt, which is going to be equal to the position function evaluated at b minus the position function evaluated at a. This definite integral represents the net change in position, which is what's referred to as displacement of the particle. It's the difference between the ending position minus the starting position on the straight line. Let's look at an example of this. Suppose we have the velocity of a moving particle along a line is given by v of t equals t squared minus t minus 12, where t is in seconds. What is the displacement of the particle on the time interval 1 to 5? So we're looking for the displacement, in other words, the net change in the position. So the displacement according to our net change theorem should be the definite integral from 1 to 5 of v of t dt. This is going to be the definite integral from 1 to 5 of t squared minus t minus 12 dt, which is equal to t cubed over 3 minus t squared over 2 minus 12t evaluated from 1 to 5. We can go ahead and plug this in. We evaluate that antiderivative at the upper limit of integration. We get 5 cubed over 3 minus 5 squared over 2 minus 12 times 5 minus 1 cubed over 3 minus 1 squared over 2 minus 12 times 1. This is going to be 125 over 3 minus 25 over 2 minus 60 minus 1/3 minus 1/2 minus 12. Let's go ahead and distribute this subtraction through so we can kind of combine some like terms over here. That become a plus 12. 125 over 3 minus 1/3. That'll give us 124 over 3. Negative 25 halves plus a positive 1/2. That will give us negative 24 over 2, which would be the same thing as negative 12. We still have a minus 60 and a positive 12 term. The 12s cancel, so it ends up being equal to 124 over 3 minus 60 over 1, which would be 124 over 3 minus 180 over 3, which will give us negative 56 over 3. That would be the total displacement of the particle from t equals 1 to 5. Let's now go ahead and find the total distance traveled by the particle on the time interval. For the total distance, one of the things that we need to consider is that even if a particle starts at one place and ends at another, the way in which it can do so might not be linear, in other words, straightforward. It can oftentimes kind of go back and forth. So sometimes it might go to the right, and then to the left, and then maybe back to the right again. If you look at the displacement only discusses the difference between its starting position and its ending position. Yet the total distance traveled would be much greater in this case because they had to cover this length, and then they backtracked, and then they covered this length. So for the total distance traveled doesn't really care about the direction. So it's going to be the integral from 1 to 5 of the absolute value of v of t dt. To find this integral, we need to discover where is the function t squared minus t minus 12. When is it positive and when is it negative? To do that, let's first begin by setting it equal to 0 to see when this thing would be equal to 0 at. We can go ahead and factor it. This would be t minus 4, t plus 3 equals to 0. We get two solutions, t equals to 4 and t equals to negative 3. So these would be the points in time when the velocity would be equal to 0. We can take these points and plot them on a number line. Negative 3 would be here, 4 would be here. And then what you could do is use kind of like what we did in the last section. We can do a sign chart here, plug in some test points to see the value for the velocity. I will skip to the chase, but if I plug in negative 4, I know that the velocity is going to be positive here. The velocity is going to be negative in between negative 3 and 4. And the velocity will be positive for values of t greater than 4. Now, what does that have to do with our total distance here? Well, the answer is the velocity changes sign within this interval from 1 to 5. If you look at the velocity between 1 to 4, that would be in this region here where it's negative. But after 4, and until the end of our interval, which is 5, we see that the velocity function is going to be positive. So this is going to have a huge impact. Because the velocity is negative between 1 to 4, its absolute value is going to be equal to the negative of v of t, which is going to be the negative of t squared minus t minus 12 dt. And it's positive from 4 to 5, so its absolute value is just equal to itself, plus the integral from 4 to 5 of t squared minus t minus 12 dt. Now that we have it set up, we can kind of go ahead and work through this. I would probably begin by distributing my negative sign through here. Make this a plus, minus, plus, plus. We can go ahead and find our antiderivatives. This would be negative t cubed over 3 plus t squared over 2 plus 12t. And this is going to be evaluated from 1 to 4 plus the antiderivative of the second part. That's going to be, again, t cubed over 3 minus t squared minus 12t, and that's going to get evaluated from 4 to 5. we go ahead and substitute everything in, so we need to plug in the upper limit of integration first, negative 4 cubed over 3. And just to save some time, I'm going to do some of these intermediary steps along the way. When we plug in the upper limit of integration, I plug in 4. We're going to get 4 cubed is 64. So that's negative 64 over 3. 4 squared is 16. Divided by 2 would be 8. 12 times 4 is 48. Subtract the lower limit of integration. Should give you a negative 1/3 plus 1/2 plus 12. Let's look at the second piece of this. Plug in the upper limit of integration. 5 cubed is 125 over 3. 5 squared is 25. Negative 12 times 5 is negative 60. Subtract, now we have to plug in 4. 4 cubed is 64, so it's going to be 64 thirds. 4 squared is 16, so it's a negative 16. And then negative 12 times 4 would be negative 48. So this is what we're going to have all together. Let's see if we can kind of go ahead and simplify this. I have negative 64 thirds plus 8 and 48 make 56. Distributing the sign in, I'm going to have a positive 1/3 minus 1/2 minus 12 plus 125 thirds minus 85 minus 64 thirds. On the inside, negative 16 and negative 48 would combine to give a negative 64, but then the negative and the negative will turn that into a positive 64. So we're here. Let's now go ahead and combine all of our like terms. For the whole numbers, we have 56, negative 12, negative 85, and 64. 56 minus 12 minus 85 plus 64. That would give us 23. We have negative 64 thirds and another negative 64 thirds. That would give us a negative 128 thirds. Negative 128 thirds plus a positive 125 thirds will give us negative 3 thirds, or just negative 1. And then we have this one extra term of just minus 1/2. So in total we get 22 minus 1/2, which would be 21.5. Or if you wanted to, you could even, do an improper fraction. But the total distance traveled here would be 21.5, and that was in terms of feet. That would be our total distance traveled.